Hi, and welcome to the lecture 4 of the glacier part of Geos 119-120. We're going to talk about the glacial hydrology, and that's going to be part 1 because the next lecture is part 2. Those lectures might be pretty lengthy, and there's a lot of stuff, especially it might be a bit of a confusing lecture, but I'll try to be as clear as possible, and absolutely let me know, as always, if you have trouble with something. Absolutely never hesitate to reach out, basically. So just a small review of last lecture. We saw different kind of motions in the glacier. So internal deformation, basal sliding, and that is kind of those models that are combining those two types of motion, where you have the ice that's overlaying some deformable sediment, and depending on where you place that lubrication layer, that is like a very thin layer of water, then you will have different outcomes. So let's say that you have a glacier that's sitting on top of hydrated permeable sediment, and all of that is sitting on a thin layer of water, then all of that will move pretty fast. And if the ice is sitting on sediments that are basically dry, deformable but a bit dry, then all of that will move much slower. We also saw the velocity profiles of the ice in the glacier, and really insisting on the fact that the ice flows the fastest at the surface of the glacier and the furthest away from any friction. So in the center line of the glacier, where it's the furthest away from both the bedrock and the walls of the glacier. And yeah, that's what the velocity profile of the ice looks like from a side view, where it's the slowest at the interface with the rock. That's what a cross-sectional velocity profile looks like, with, again, concentric circles. The furthest away you get from any kind of friction, and the faster you are. So yeah, that's just a small summary of the ice flow. As I said, ice velocity is fastest at the surface along the center line and near the ELA. I don't know if you recall that figure showing ice velocities in Southeast Alaska for some glaciers, where for valley glaciers, typically the ice will be the fastest close to the ELA. And we saw the particular case of Tidewater Glacier, of the Herbert Glacier in that case, where fast velocities can be sustained to the terminus, because the terminus is touching the water, touching the ocean. The speed of a glacier increases the thicker the glacier is, the steeper the glacier is, and the warmer the glacier is. Thicker because you have more material that's being pulled down by gravity. And that's the reason, by the way, why the valley glaciers are usually fastest at the ELA, because that's the point where you have the most amount of material upstream that's kind of pushing down. And also, if you put a glacier on a very steep slope, well, expect it to slide really fast. And the warmer the ice is, the more deformable it gets. And if the ice is at the melting point, it will melt, it will create water that will then lubricate the sliding area, and therefore the glacier will flow faster. What causes ice to deform internally? Both subglacial water flow that lubricates the ice, the sediment deformation, and the weight of the overlying ice. Can complete that by saying overlying ice, snow, fern, and rocks, if you want. So yeah, I think that's the last slide of this first section.